Well, hello. I'm David Andes from the University of Wisconsin. Unfortunately, still at the University of Wisconsin, where we have snow and it's minus 6 degrees Celsius today. Sorry I couldn't be there with you. I'm sure Jesus feels the same. I was asked to discuss antifungal susceptibility testing as it relates to Aspergillus and the CLSI approach and recent decision on breakpoints for voriconazole. So there are 4 data sets that were considered in deliberating the susceptibility breakpoint, and I'll review each of these and then share with you the discussion and eventual breakpoint decision. So these include data from preclinical infection models, examining pharmacokinetics and pharmacodynamics, clinical therapeutic drug monitoring outcomes relative to typical MIC distributions. Third, the impact or clinical outcome of patients infected with organisms with MICs outside the wild-type range. And finally, clinical pharmacokinetics and pharmacodynamics with voriconazole in patients with invasive aspergillosis. So we'll begin with the pharmacokinetics and pharmacodynamic data. And to introduce that, we'll begin with the concept and hypothesis underlying these types of data sets. Simply put, PKPD examines the relationship between drug concentrations, typically in the serum, relative to a measure of potency, in this case the minimum inhibitory concentration, and patient outcome. It's hypothesized that there's an optimal drug exposure relative to this measure of potency that will optimize patient outcome. For the antifungals, there are 3 pharmacodynamic profiles, and for the triazoles that we're considering today, it's the total area under the concentration curve relative to the MIC that is the pharmacodynamic parameter that we wish to optimize. So let's get right to the data. First, the preclinical PKPD data. This first data set is actually data from our lab, not with voriconazole, but with posaconazole in an immunocompromised mouse model of pulmonary aspergillosis, where we examined the effect of a wide dose range of posaconazole on the burden of organisms in the mice of lungs at the end of therapy using quantitative PCR. We used 4 strains in these models. The hollow symbols represent strains with wild-type MICs for voriconazole and quite low MICs, again, usually at 0.25 micrograms per ml. We also included 2 strains that have CYP51 mutations and posaconazole MICs of 2 and 8 micrograms per ml, respectively. And you can see 2 things. First, with the wild-type strains, we see a nice dose response. Also with the posaconazole strains with higher MICs, we also see a dose response, but the dose response curve is shifted significantly to the right. I'll also draw your attention to that vertical, on my screen it's a reddish maroon bar, and that represents the posaconazole exposure that would be expected in patients. So you can see here with a posaconazole exposure in mice that would mimic that seen in patients, we had very little effect on the organism burden, demonstrating in this case that triazole resistance does matter. This next data set also is data from a mouse model of Aspergillosis, also in immunocompromised animals, but this is a disseminated tail vein model where patients were treated, in this case with voriconazole for 14 days, and the output was, as you can see on the y-axis, survival. They also demonstrate a nice dose-response relationship as you increase the voriconazole AUC to MIC, moving from left to right, and they observed 50% survival at an AUC to MIC of a little over 10, and maximal survival, or 80% survival, at an AUC to MIC near 25. So this data set includes 2 strains that would have been classified as drug susceptible with very low MICs, 0.125 micrograms per ml, and 2 strains that had higher MICs outside of the wild-type distribution with MICs of 2 micrograms per ml. When they considered the AUC to MIC of voriconazole that was associated with 80% survival, and they looked at that AUC to MIC and estimated the AUC to MIC in patients, they would have predicted a susceptible breakpoint at an MIC of 0.25 micrograms per ml, again based upon average human pharmacokinetics and pharmacodynamics. So the first data set using a preclinical PK/PD model that suggests a susceptibility breakpoint. This next data set moves away from animal infection models and into an in vitro infection model where the output is a galactomannan level, and they were identifying the voriconazole exposure associated with maximal galactomannan suppression. And they identified that as voriconazole AUC to MIC of 55, so a little bit more than twice that identified in that animal infection model. And this also corresponded to a trough voriconazole concentration relative to the MIC of 1.68. They also used 4 strains in these studies, 2 susceptible, 2 resistant, with a very similar MIC range. What the figure above demonstrates is how they then use this information to attempt to identify a human susceptibility breakpoint for voriconazole. So on the x-axis, you have a range of voriconazole MICs, and the solid square symbols represent an MIC distribution, a typical MIC distribution. On the left, on the y-axis, you have the fraction of patients using Monte Carlo simulation, considering human pharmacokinetics, that would have achieved a trough to MIC ratio of 1.68. Again, that in their model that was associated with maximal galactomannan suppression. And from this, you can see then the solid circles and line show you then that fraction of patients that would have achieved that pharmacodynamic target. And using 90% target attainment, they identified a susceptible breakpoint of 0.5 and a resistant breakpoint of 1.0. So fairly similar to that identified in that first preclinical animal infection model. Next, the committee considered clinical therapeutic drug monitoring with voriconazole relative to voriconazole and Aspergillus fumigatus MIC distribution. So as you're all aware, voriconazole is unique in its wide variability in pharmacokinetics among patients. Early on identified in cancer patients. There's a data set on the left. And on the right is data examining the impact or trough voriconazole threshold predictive of patient outcomes. And the red symbols represent data from our group that found that patients that had an a voriconazole trough concentration greater than 2 was associated with optimal survival. In a subsequent data set that identified a voriconazole trough concentration of greater than 1 associated with clinical success. So if one considers these trough concentrations relative to a typical voriconazole Aspergillus fumigatus MIC distribution, as shown here in data from the San Antonio group, we find an MIC 90 of 0.5 micrograms per ml. Again, mostly drug-susceptible isolates. So if we consider this MIC distribution relative to that trough, optimal voriconazole trough concentration of 1 to 2, so that 1 to 2 relative to that MIC 90 of 0.5, we come up with a trough to MIC value of roughly 2, which is interestingly quite similar to that was identified by William Hope's group in that in vitro galactomannan suppression study. So if we then consider the trough concentrations that we can achieve in patients, we can back calculate what the maximal MIC that we would achieve that trough to MIC concentration ratio. So if you had a trough to MIC of 1, you would predict successful treatment in patients infected with organisms with MICs as high as 0.25. Obviously, that doubles as you move to a trough concentration of 2, and doubles yet again if you move to a trough concentration of 1.0. So dependent upon the pharmacokinetics of voriconazole, but again, I would say at least in our hospital, we're shooting for a trough concentration of 1, and so the susceptibility breakpoint would be less than or equal to 0.25 based upon the TDM data. Next, let's look at the clinical outcomes in patients infected with organisms with higher MICs. So here's a graph demonstrating, this is now several years old, demonstrating the percent of Aspergillus fumigatus isolates with elevated voriconazole MICs across the world. You can see quite variable. But what's also included in these publications, in many of these publications, is patient outcome in these patients. And unfortunately, poor outcome is described for the great majority, with mortality rates exceeding 80%. There have been 2 studies that have looked retrospectively at a larger population of patients infected with organisms with higher MICs. This is data from Europe, looking at over a 5-year period, 2011 through 2015, almost 200 patients with Aspergillus fumigatus infections for which there were MICs. 37 of those isolates fell outside the wild type range. And here's a Kaplan-Meier curve looking at the probability of patient survival depending upon infection with strains in the wild type distribution, colored here with the blue line relative to the dashed red line, which were patients infected with strains outside the wild type, and you can see they fared quite poorly relative to those infected with the drug-susceptible strains. And so here, these resistant strains were categorized as organisms with MICs of 2 or greater. There's a single similar publication from a single center at MD Anderson, 100 patients, again, a fair number with MICs outside the wild-type distribution, but none were highly resistant and none had CYP51 mutations identified. This was over a 15-year period, and here they did not demonstrate an impact of these higher voriconazole MICs, perhaps not enough in the high MIC range. The final and I think most impactful data set that we discussed was that looking at voriconazole pharmacokinetics and pharmacodynamics in patients. And this is a publication from Peter Troke and William Hope, in which they looked retrospectively at the impact of voriconazole AUC to MIC and trough concentration to MIC from the 9 voriconazole clinical trials that included over 800 patients and more than 150 infected with Aspergillus. And what you can see on the left is the relationship between voriconazole plasma concentration and likelihood of clinical success. So you can see that the likelihood of success increases until you get to a concentration just a little over 1, which is probably not surprising given the TDM data sets I just showed you. When one then incorporates MIC, again, you see a plateau at a trough to MIC concentration of about 2.5, so not that different than the TDM estimates in the exercise we just went through. Also fairly similar to, again, the in vitro trough to MIC data sets. This would again correlate with 65% success, and if one considers this trough to MIC concentration the maximal MIC that you would predict successful treatment would be an MIC of 0.5 micrograms per ml. So what did the group agree that this data told us? We agreed that elevated voriconazole MICs in Aspergillus matters for in vitro and in vivo infection models and also for patients. The MIC and clinical outcome data we thought clearly identified an MIC above which patients were likely to be more likely to fail therapy, and that was a MIC value of 2. As far as susceptible breakpoints, the in vitro and in vivo models were fairly congruent, and susceptible breakpoints ranged from 0.25 to 0.5. Similarly, the TDM and MIC90 data puts you in a similar range as far as susceptibility. And fortunately, the clinical PK/PD data set also told us that once you got to an MIC of greater than 0.5, you were more likely to fail. In the end, I think this latter data set carried the day. As you can see, the vote was for a susceptible breakpoint of less than or equal to 0.5, with the option for an intermediate category of 1, although there was quite a bit of discussion here. But since many are using voriconazole therapeutic drug monitoring, this would give clinicians the ability to increase doses and hopefully trough concentrations in these patients. And there was pretty strong consensus that patients infected with isolates of 2 or greater should be categorized as resistant. Again, the sole debate was whether or not this could perhaps be shifted down to 1, but again, because of the ability to increase doses and hopefully increase trough concentrations, it was felt important to give clinicians this option. So that is our CLSI discussion, and I wish I was there to take your questions, but if you'd like to email me, I'd be happy to converse in that way. I hope you guys have a great rest of the meeting. I'm sorry I couldn't be there to enjoy it with you. Thank you.